Hi, hello. Welcome to the Physionic podcast. If you're new here, my name is Nicholas Verhoeven. I am currently pursuing my PhD in molecular medicine, and today I've got two topics to discuss. The first one is a bit of a history, I guess you could call it lesson, or more of a discussion based off of a book that I'm going through called The Great Influenza. I think that's what it's called. It's been a really interesting read, and I've learned quite a bit in terms of the history of medicine. And I guess I have some thoughts when it comes to kind of the incredible nature of how quickly our society, or I guess our species really, has evolved in terms of our thought process around medicine. So I kind of wanted to discuss that and give you a bit of history on that. And then the other topic that I wanted to discuss was a little bit on zoonotic origin of viruses. So I have this this piece of content that I released several weeks back now when the whole coronavirus thing was going on. Well, it's still going on, but when it first hit and everybody was curious about it, and it was discussing if the virus is man-made, and people were calling into question the zoonotic origin of the virus, meaning that it came from animals. So I'd like to discuss that and kind of give a little bit of perspective on how likely something like that is to occur. So without further ado, I'll jump into those two topics. Of course, I'll have timestamps for you if you're only interested in one. And so let me jump into a little bit on kind of the changes in medical practice and kind of the changes in our thought process over time. I found this to be really, really interesting. I didn't really expect it to be in this book, but as I've been going through it, it's been a enlightening read for a number of reasons. I've understood that science has had a dramatic impact on how well our civilizations, how well our species has been able to survive and improve in all these different areas. And that's not necessarily just towards medicine. It can be towards any area of science. But especially in the 1800s is when things really ramped up and where we really understood medicine and understood pathology or virology, bacteriology, how these different systems or how these different outside forces were affecting our immune system. And we really ended up understanding how our immune system works as well. So it's a little scary to think that what was going on in the 1800s was considered acceptable practice when it came to medicine. But on the other hand, the changes that occurred, and I'll go into what those changes were and what acceptable practice was in just a second, but that the changes that were implemented are now kind of common practice, and the fact that they haven't been around for very long. And yet we know tremendous amounts of information just over the last 120 years. So just a little over 100 years of us implementing these practices that I'll be touching on. So what exactly am I talking about? Well, in the past in the United States, there were about 150, from what I remember, about 150 schools of medicine. So hospitals that were linked or just medical schools. And interestingly, it was considered like a trade school. So it was actually easier to get into a medical school than it was to get into like a liberal arts college to study some sort of liberal art. And not only that, it was so easy that you didn't have to have any science background whatsoever. So immediately from high school, you could go into a medical school or be accepted into a medical school. And the entire system was just based off of lecture. So you would just learn maybe like the anatomy of different things, but you would never actually have any hands-on experience, which is a pretty scary thought, right? If you go through, I think at this point it was like 2 years or something like that, 1.5 years, 2 years, something along those lines. These students would graduate, and then they would either undergo an apprenticeship where they would learn more under a physician, a quote unquote qualified physician, wherein this individual would then give or kind of oversee the student's progress in terms of hands-on experience, so actually working with patients. Now, the issue is that these students were technically graduating with a license in medicine or a degree in medicine without necessarily having to go through that process of going through and going through the apprenticeship process. So you had some students that were just opening up practices, even though they had never seen a patient, never touched a patient, never done anything. They only knew a bunch of kind of loosely formed ideas or just kind of a general theoretical understanding of medicine. So that's certainly a worrisome trait to have, and that persisted into the late 1800s and the early 1900s, actually. So yeah, I mean, we're talking just a little over 100 years ago, doctors did not need to have any experience with patients. You can imagine that led to a lot of terrible diagnoses, and certainly I'm sure people suffered. I'm sure the general population suffered quite a bit as a result of that fact. Now, that was the case in the United States. However, things were considerably different in Europe, especially in Germany and France. Germany was certainly a forefront when it came to having laboratory-based research that was driving medical practice. So that was another issue with the American system, was that none of it was backed by laboratory research necessarily. So none of the medical schools were doing any laboratory research. Like I said, it was more of lecture-based. So it was essentially all lecture-based, so you had no hands-on experience. But in Europe, and specifically in those two countries, but certainly other areas as well, like England, the idea was that the medical schools would be based on laboratory research. And I think it's important to point out that doctors don't just know things out of nowhere, out of the blue. They learn these things based off of studies. And where do studies come from? Well, they come from scientists, medical scientists, that specifically pull together isolated pieces of information, study after study after study, until you have a body of literature that then practitioners, actual medical doctors, MDs, can then go forward and start trying that after clinical trials to test that on, not really test it, I shouldn't say test, because at that point it's been rigorously tested in a petri dish, it's been tested in animals, it's been tested in a variety of animals, it's been tested over time, it's been tested in small groups of individuals, it's been tested again in larger groups of individuals. So it's gone through 5 or 6 different tests to test if something is functional, if some treatment actually works. So at this point, then the practitioner is feeling pretty confident that when they give this treatment, that it's going to be helpful. So in Europe, they were doing things based off of laboratory research, and they were way ahead of the United States in terms of their medical schools were just a much better quality. And as an example of this, you've got these really famous scientists in biology and medicine, known as like Louis Pasteur, who I don't believe he invented vaccines, but he was responsible for some really key vaccines. And one of his biggest contributions, another contribution is pasteurization, but one of his biggest contributions is attributing germ theory, or coming up with germ theory. So germ theory is essentially that some diseases are related to pathogens, that they're related to microbes. And the infection of a microbe in the body can lead to a pathology, can lead to some sort of problem or some sort of disease. Now, we humans had known about microbes existing for, I believe, about 200 years before that, maybe more. I believe it's Leeuwenhoek. I'm not entirely certain about that, but there was a person who, I believe he invented the microscope, found that there are microbes that exist. However, nobody actually attributed those microbes to getting people sick until Louis Pasteur ended up showing that that's the case. So he experimentally showed it, and that's kind of the point that I'm trying to get across here, that he wasn't just theoretically thinking about something, he was actually also testing it and coming up with conclusions that, yeah, I mean, this is truly the case, that a biological being can get infected by another biological being, and then that leads to pathology that can lead to disease. Another really famous person, and he was from France, another famous person is Robert Koch, who is sort of considered the father of bacteriology, and talked about and really discovered the causative agents of cholera and tuberculosis, and again just kind of worked off of Pasteur's germ theory. And you've got a bunch of other examples as well that kind of came out of those two countries specifically, but again, like I said, all of Europe was really kind of taking a step forward. The point being that it's really important to base things in a scientific method. And what's really crazy is that, you know, science had existed, I guess up to that point had existed for about 300 years, maybe 350 years. And now it's existed for about 500 years. So it's pretty stunning to me that it was in just merely 100 to 150 years, we've gone from understanding, something seemingly basic like germ theory, right? And now we're figuring out ways of targeting the molecules within germs to incapacitate them, or to figure out ways of dealing with, let's take an example like bacteria, right? We end up figuring out that antibiotics are effective through like different treatments that you can use. There's different antibiotics that are helpful in nature that can actually fight off bacteria. And I think the only way that we can really come to that conclusion is based off of the research, not just the theoretical understanding, but the actual research to prove some of, or essentially all of these ideas. So it's really a small amount of time, if you really think about it, that there's been this explosion of understanding in medicine that's related to biology. Once we understand the underpinnings of how biology functions and biochemistry and all these different areas, that led to this explosion in our ability to extend lifespan and to increase quality of life, and I mean all these different things. So it's really, really remarkable that in just such a short amount of time that we're at the point that we are now, and I'm definitely excited to see what's going to happen in the future. Okay, so let me go back to the United States. So like I mentioned, there are about 150 schools, and they did not use a laboratory method. So they essentially just kind of looked at things or just kind of theoretically thought about it and then just kind of taught it that way, which is certainly scary when it comes to actually working with patients. Meanwhile, in Europe, they were using lab techniques and trying to use the replication process of, okay, it applies here, does it apply here? Okay, it applies here, okay, does it apply, one strata higher? And that, of course, ends up permeating into the public sphere so that people can take advantage of all these different treatments that are coming out of Europe. And let me tell you, in the 1800s, there were a ridiculous amount of treatments that were coming out of Europe. So going to specifically Johns Hopkins University in the United States, they ended up deciding, well, we want to build a school that's going to be based on laboratory or on science. So, of course, that had to do with laboratory research. So I'm not going to go, there are a number of people that were involved in that, but one of the key ones is a person by the name of William Welch. And William Welch had been studying in Germany, had decided that I believe he went to Yale and studied medicine, and he felt like his education was just really easy. Like it didn't feel like he was educated, which is a weird situation to find yourself in. So he decided to go to Europe to kind of bolster his education and make himself feel like, okay, I'm actually learning about science. I'm learning how the scientific method functions. So he did that, and he went to Germany, and he went to a bunch of different laboratories and learned from a bunch of different people. And I believe he did end up actually learning from Robert Koch, the bacteriologist I mentioned earlier, by going to his lab. And then the person, I can't remember his name, but the person that was looking to open Johns Hopkins University, or build this unique university, at least unique to the United States, ended up running into William Welch and found him to be really enchanting, that he was a perfect fit for exactly what they wanted to do. So William Welch, who had some experience at this point now in Germany, ended up moving back to the United States. And he struggled a little bit trying to get this idea of, hey, we need laboratory research in schools. Otherwise, physicians aren't going to understand what's going on. And we also need people to be more hands-on when it comes to clinical practice, so that they actually have experience with patients and seeing people and diagnosing and things of that nature, not just looking at theoretical stuff. So eventually he was hired to, I think he was the first professor of Johns Hopkins University, and then they didn't open for a number of years. So he was offered, tons of opportunities in terms of lab space, and, they really wanted to make this a European model type of university. But he ended up going back to Europe for a while longer just to learn some more until the school was ready to open. So eventually it did open, and it became certainly the hardest school to graduate from. But suddenly the bar, the standard, had translated from Europe to the United States. Now there was one school that was working really hard to make sure that all of their students would graduate with a background that was based in actual practical knowledge, but also in research, actually having done some research, so they understood the scientific process and could speak on it intelligently. So Johns Hopkins ended up becoming the gold standard, even over schools like Harvard. So it was far and above everyone else. And as I mentioned before a few times, that there are 150 schools, so quite a lot of schools. Well, it turned out that eventually there was this man named Abraham Flexner that was hired to survey these schools. And he went to all 150 schools and ended up surveying them and kind of coming up with this report saying that, okay, these schools are in the C category, these schools are in the B category, and these schools are in the A category. A meant that they were up there with the gold standard, that they were exactly what they should be. This is what's considered now, according to the European model, and now the Johns Hopkins model, which took the European model and implemented it, that these schools fit that model, and therefore they don't need to make any drastic changes to their structure of how they teach and how they go about having these graduates come out of their school. The B schools were acceptable, but had to make some changes in terms of how they went about their curriculum and how they went about having these graduates. So, and then the C schools were essentially schools that he recommended that they should be gutted completely and be completely rebuilt from the ground up. And so he found a total of 5 schools in the A category. So 5 schools made it to the A category. I believe, from what I remember, it was about 20 or so were deemed revisable, so they were in the B category, and all the other schools were to be gutted. And shockingly, people took that to heart, and they just based off of this one man's conclusions, based off of his surveying of all these different schools, they ended up following that thought process, where the states started to ask for, you need to fulfill these requirements, and then we'll recognize you as a practicing doctor. And of course, you can imagine that these these standards were based off of the Johns Hopkins model, the gold standard model, the A style, A-list model. Now, that put a lot of these other schools that for 100 years prior had been acceptable, had been like, hey, we're just accepting students, and then they graduate, and then, as I said, they wouldn't have any experience, actual experience working with patients. So that was really problematic, because suddenly the standard was something that they couldn't meet. So students were graduating and they couldn't practice, because their degree was immediately invalidated by the fact that the states were starting to crack down on that style of teaching, that style of school. So suddenly all the schools had to either shut down or completely gut themselves and change their entire curriculum to meet this standard, which is a really powerful statement, to think that one person can go around and and apparently Abraham Flexner was an incredibly critical person. So he was very harsh about his critiques of different schools. And it's pretty telling that, one school, Johns Hopkins University, looks around, as opposed to just saying, oh, we're going to do it this way, and we're going to do it the same way as everybody else, and maybe we'll make a few tweaks here and there, and that's going to make us unique. No, they decided, well, we're going to think about this for many years. It was a number of years that they really thought about it, how they wanted to go about this process. And they ended up looking at Europe, and they found, wow, Europe's coming out with all these inventions. Vaccines are coming out of there. They're coming out with germ theory. There's all kinds of different things, and the population is getting healthier and healthier and healthier, because, or at least in correlation with all of these changes. So we want to do that. So they just, this one school had a massive impact across the entire country, and within 20, 30 years, all the schools had to fit that standard that one school had. So it's a really, really cool, I think it's a really cool story. And it tells us that it's just a little over 100 years that the doctors that we have today have had to follow this stringent style of doctoring, of just being part of this kind of, I don't want to call it a brotherhood, but an association that is based on science education and laboratory research itself, as well as hands-on practice. So you can thank these individuals kind of going forward if you ever have to end up in a hospital or ever have to talk to your doctor, because your doctor is essentially being it has their education based off of that style, that gold standard style that wasn't around just a little over 100 years ago. Anyway, I thought I'd share that because I thought it was really, really interesting. And now I'm just going to briefly talk a little bit about the flu, or really about zoonotic viruses, but more specifically around the flu, because that's what this book ends up talking about, and kind of throwing in some of the stuff that I've learned as well. So I mentioned at the beginning that a zoonotic virus is a virus that can jump, quote unquote, jump from an animal to a human being and infect that human being. And I've seen a lot of people be really skeptical as to how that happens, or what are the causes of something like that. And the reality is, like, there are a few different ways it can happen, and I haven't looked into it. I haven't looked into all the different ways that this happens. But one way is that let me just say, I don't think that people really understand how much this happens. This isn't something where you're looking at like an isolated situation and you're saying it's just happening here. It's happening all the time. Every time you're in contact with an animal, it's happening. It's just not affecting you. That's kind of the point, the big point I'm trying to get across here. So let me give you a few numbers here. With the flu, which is an RNA-based virus, and this is going to change based on the type of virus. If you're talking about like a DNA-based virus, it's going to be slightly lower, or it's going to be actually pretty massively lower than an RNA-based virus. But an RNA-based virus doesn't have proofreading mechanisms to make sure that mutations are corrected. As such, that means that whatever mutations occur, which happen incredibly frequently, those are going to get translated into the new virus. So if a cell, let's say an animal cell, is infected by a particular virus, let's say a flu virus, then that cell will take up the virus, and then it'll start creating more virus based off of an RNA template. Now that RNA template can get bombarded with all kinds of different mutagens or different outside factors that can lead to a mutation within that RNA template. And those don't get fixed, unlike DNA, which do get fixed, and therefore you don't have as much mutagenesis that occurs. So a cell will produce anywhere between 100,000 and 1,000,000 viruses in actually less than 24 hours, but let's just say 24 hours. And then the cell will typically burst. So once it bursts, you have this release of anywhere again between 100,000 and 1,000,000 viruses. Now the thing is with an RNA-based virus is that a lot of the viruses are completely different from one another because they're mutating constantly. So you have essentially kind of a competition between the viruses, and eventually one virus or maybe a few viruses will affect other cells. So it's not like all 100,000 viruses or 1,000,000 viruses will affect all cells. Some of them will actually out-mutagenize themselves, if that's even a word. Will essentially, whatever advantage they had, they will eliminate their own advantage. It's not like they're sitting there choosing it. It's just the way it works because of how the mutations are occurring. So a lot of these viruses will become inert. So they get released from the cell. I mean, they were effective in the cell, and then once they're released from that cell, once the cell bursts and they end up trying to attach to other cells, they end up finding, not that they're sitting there thinking about it, but they end up finding that they can't enter the cell because they have a mutation it's not going to function. It's not going to allow them to enter the cell anymore. And that's just one example. There are a lot of other examples. But you can have mutations that lead to things that affect other cells. So let's say if 1% of the viruses end up bursting out of a cell then affect other cells, then you have more cells that are being infected, and so on and so forth. So let's just imagine that with those numbers in mind, 100,000 being released from just a single cell within a 24-hour period. Now think about 1,000 cells being infected, which is an incredibly low number. I mean, your body's made up of trillions of cells. So, and maybe people don't think about that too much, but 1,000 cells is pretty much nothing. It's not even a drop in the bucket. So let's say 1,000 cells get infected. That means that you're getting 100,000 times 1,000 within a 24-hour period. So that leads to anywhere between 100 million viruses bursting out of these cells, all the way up to 1 billion viruses bursting out of this tiny population of cells. And in all reality, if you're talking about a systemic issue, you're technically talking about probably, many, like thousands and thousands of billions of viruses releasing into the system, into your body, or in this situation, in an animal's body. So it's affecting these animals, but it's not affecting us, right? The problem is that this is happening all the time. Like if you actually have an infection, but there are situations where it's kind of sub-threshold, where you're getting, maybe you're infected, but you don't know that you're infected, or it's this virus may affect like just a few cells, but it doesn't affect like the entire population of cells, and therefore you don't you experience any symptoms, and your body just takes care of it. It's not a big deal. But the point being that it's always happening, and when it does happen to a degree that you're actually feeling symptoms, it is massive. trillions and trillions of viruses are being shed. It's called a viral swarm when they release from or burst out of a cell. So if you have an animal that's sick and you may not even recognize that it's sick and you're around it, I mean, even for a few minutes, you're gonna take up a whole lot of viral load. You're gonna take up a whole lot. I mean, we're talking millions of viruses are flooding into your body. Now, that said, the reason why it doesn't get you sick is because those viruses are primed to infect the animal. They're not primed to infect you. But like I said before, and why I was telling you about these mutations, is that what if you have just a single virus of millions that are infecting you, just a single one, and it's, they're all very different from one another, but they're all within that family of influenza viruses. You have one virus that just finds its way to just one of your cells, and it has just the correct mutation, that it infects your cells. And remember, if it infects one cell, and that cell is not capable of fighting it off, because sometimes they are, but if it's not capable of fighting it off, then from that one virus in that one cell, you have 100,000 to 1,000,000 more viruses that are being produced. And again, of course, many of them will kind of outcompete themselves and end up leading to an inert virus, but you'll still get a large population of that, a family of that virus, which will affect all your other cells, and there it starts to propagate. So viral load matters considerably, and if you're in contact with animals. So sure, it doesn't happen very often, but we are incredibly lucky that it doesn't happen very often, because of the number of chances that are present for it to happen often there aren't enough numbers for me to describe how often we have these exchange of these particulates between us. I mean, between humans and humans, but certainly in this situation, because I'm trying to focus on zoonotic viruses, zoonotic origin, that can lead to a transmission from an animal to a human. It's still very rare, even though I'm throwing out numbers of billions of possibilities. A lot of them self-select out so that they don't affect, and it kind of has to be a perfect storm. Like, you do have to be around the animal as well. So hopefully you're getting some understanding of, it's rare, but it's still possible. And I think a lot of people don't understand that. They don't really understand how an animal can infect a human being. And then I think everybody understands how humans can then infect humans, because that mutation just persists, or that virus persists, and it affects a whole lot of other humans. Now, granted, one of the scary things about an RNA-based virus is because of those quick mutations, that it can jump to another human, and that human can have, let's say it's an identical twin to the first person that was infected, but the first person that's infected passes it on to the second person. Now they're infected. Now they may have an RNA mutation in one of the viruses that they end up taking up that leads to that virus becoming deadlier or becoming less deadly as well. That could be the case as well, but maybe it transmits more easily, or there's a lot of different variables that are taken into consideration. So hopefully this gives you a little bit more perspective on the whole process, kind of in general, not necessarily just like, I'm not necessarily saying just coronavirus, but just saying in general, zoonotic origin of viruses can occur because of this mixing that happens, of this constant mixing that's occurring between these viruses and how they're affecting our cells. So with that, that's where I'll leave it. Hopefully you found this informative. I mean, it's a little bit different, right? I'm not necessarily giving you any applicable information really, but hopefully you found the history a little interesting, because I found it really interesting, and it kind of gives you some perspective on where we've come over just 150 years or less than that. And then kind of using the influenza virus as an RNA-based virus, but coronavirus is also an RNA-based virus, and kind of looking at the numbers and understanding how we have this turnover that leads to constant exposure to different virus particulates. Okay, well, with that, I will catch you next week. Have a good one, guys. Bye.